Let's take a look at this thing called the differential. If you remember, calculus was invented by Isaac Newton and Gottfried Leibniz. And they invented it independent of each other, but with the same ideas, different notation though. Remember that Newton called the derivative y prime. And when it came to Leibniz, he looked at it as dy dx. And there really is a brilliance to the way that Leibniz looked at the derivative as being this ratio of two very infinitesimally small quantities, each of them being known as the differential. And since they are two quantities and the derivative is the ratio of those two very, very small quantities, we can treat this equation as like a fraction, like a regular old equation. And in that, if I have derivative is equal to dy dx, I can multiply by that dx. So then we'll be left with dy is equal to the derivative dx. Right? And create the beginnings of what we call a differential equation. And that's really all I want to do here is to create this differential equation. We can do that by finding the derivative dy dx, and that would be equal to 6x. Then the differential equation would be dy is equal to 6x dx. Now hopefully you'd be able to jump straight to the differential equation without having to do that in between step. Just find the differential of y, which is dy, and the differential of natural log of t. So that's the derivative of natural log of t, 1 over t, times dt. Now this differential becomes more and more helpful for us the more complicated that our functions get. Here we have y being described in terms of 3 different variables, which also might be functions of some other variable. And we can find the differential of y in going term by term. So we take the derivative of 3x to the 5th, which is 15x to the 4th, and attach that dx to it. For u to the 4th, the derivative is 4u to the 3rd, so the differential 4u to the 3rd du. And for minus sine of t, derivative would be minus cosine of t, so differential dt. We could also express a differential in terms of just the d, like d parentheses u plus v would mean find the differential of u plus v. And we would do that term by term, du plus dv. If we're trying to take the differential of a product, we use that product rule, 1d2 plus 2d1. So our first function is u. And not just the derivative of v, but now the differential of v, which is dv plus v du. And lastly, our quotient rule, low d high, so v du minus high d low, u dv over the square of what's below, over v squared. But there are some examples on how you find the differential of a function.